Hi, everybody. It's Professor Mitchell. We're wrapping up Chapter 5 today. This is Poisson probability distributions. So remember, this chapter is all about discrete probability distributions. So those are probability distributions whose outcomes are only whole numbers, usually. Okay. All right. So let me tell you what this is about. Another category of discrete probability distributions. So we'll get a little more specific here in a second. Okay, a Poisson probability distribution is a discrete probability distribution that applies to occurrences of some event over a specified interval. The random variable x is the number of occurrences of the event in an interval. The interval can be time, distance, area, volume, or some other unit. So the example we're going to be doing a little later on has to do with number of Atlantic hurricanes in a year. Okay, we're going to look at I think it's a 55-year period where there were 300 some odd Atlantic hurricanes. It works out that there's an average of 5 point something per year. And we're going to answer questions like, so what's the probability of having 6 in a year? Or what's the probability of having 8 in a year? What's the probability of having at most 2 in a year? Those are the kinds of questions you can answer with a Poisson probability distribution. Okay, so this is the formula that we're going to use. This is another one of those formulas. I actually sort of remember doing this or developing this formula as a math major in school. I don't remember how to do it anymore, okay? So I'll spare you. So the probability of the event occurring x times in an interval is given by this formula. P of x, the probability of x, is mu to the power x times e to the power negative mu divided by x factorial. Okay. So what do all those numbers mean? E is a number that you have seen before if you took intermediate algebra, college algebra, pre-calc. This is the base of the natural logarithm. It's about 2.718, blah, blah, blah. It's an irrational number. It is built into the calculator. So you don't have to, you can probably get through your whole life without ever having to actually think about this decimal. Okay. Mu is the mean number of occurrences of the event in an interval. So if there's an average of 5 hurricanes a year, mu would be 5. Okay. Okay. Requirements for Poisson probability distribution. Number 1, the random variable x is the number of occurrences of an event in some interval. The occurrences must be random. Okay, so other than knowing that it happens an average of 5 times a year, for example, I have no idea when those 5 times are going to be. They're completely random within the interval. The occurrences must be independent of each other. Okay, so you know, knowing that there were 8 occurrences last year, there is absolutely no predicting how many there are going to be this year other than there's an average of 5. Okay, so the fact that we're 8 last year has nothing to do with it. And the occurrences must be uniformly distributed over the interval being used. Okay, so it's a little harder to explain what that means. It means if you look over a whole bunch of different years, the occurrences are kind of all over the place. It doesn't mean that in one particular year they can't sort of cluster. It just means that they don't usually do that. All right, they are uniformly distributed. If there's an average of 5 in a year, then that means there's an average of 2.5 in the first half of the year, 2.5 in the second half of the year. Okay, stuff like that. Okay, in an intro statistics class, you usually don't have to think too much about these requirements. But, you know, if you end up using statistics in your real life, you become a psychologist or a scientist or something, then that's when you have to think about them. Okay, so the Poisson probability distribution has only really one parameter. if you tell me mu, I can tell you everything there is to know about that distribution, okay? Now, technically, the standard deviation is another parameter, and that turns out to just be the square root of mu. So that's kind of interesting. Never seen anything like that before. All right, so like I said, a particular Poisson distribution is determined only by the mean. You tell me the mean, and that's all I need to know. And this distribution is discrete. The number or the possible values of x are whole numbers. Now, unlike the binomial random variable, there is no upper limit on what the value of x can be, all right? So think back to binomial. So example of a binomial experiment, take a 10-question pop quiz. The possible values of x are just the numbers 0 through 10. That's it. There's a finite number of them. With a Poisson distribution, there's no upper limit. So there could be 0 hurricanes, 1 hurricane, you know, I guess there could be 100 hurricanes, all right? The probability of that is really, really, really low, okay? But it is theoretically possible, okay? But it's still discrete because the possible values are whole numbers. So this is what they call countable, right? Okay, here it is. For the 55-year period since 1960, there were 336 Atlantic hurricanes. So assume that they follow a Poisson distribution. So the first thing they want me to do is find mu, which is the mean number of hurricanes per year. And then they want me to find the probability that in a randomly selected year, there are exactly 8 hurricanes. Okay. All right, so the first part of this is really easy. If there were 336 hurricanes in the 55 years, then that means that the average number per year is, we'll come back to this, okay, would be 336 divided by 55. So it actually comes out to about 6.1. Average of 6.1 hurricanes per year. Okay, so now the probability of having exactly 8 hurricanes in a year, we just figured out that mu is 6.1. So x equals 8. Don't even worry about this. This is built into the calculator, this e, okay? So I am going to exit out of this, and I am going to bring up the calculator, okay? All right, so the formula, let me see if I can do something here. Let's go back to here. It might be good to have the formula next to this. Okay. Can I make these two things work at the same time? Yeah, I think so, maybe. There we go. I think that'll work. Sorry. Please stand by. There we go. That's better. That'll work. Except why does it look like that? Hang in there, people watching at home. There we go. Okay. So here's the formula. So I'm going to start with mu to the x. Remember, mu is 6.1. X is 8, okay? So there's that part. Now, E, okay? E is built into the calculator. If you go second, and then this button right here that says ln for natural logarithm, okay? So on my calculator, when I press that button, it's asking me, okay, e to the power what? It assumes that I want to raise e to a power, because that's almost all we ever do with e, all right? In intermediate algebra, pre-calc, practically everywhere we use e, the only thing we ever do with it is raise it to a power, all right? So be sure you hit the negative button and not the subtract button. 6.1, okay? And now I have to divide that by x factorial. So I'm gonna go divide 8 And then remember, factorial is under the probability menu. On this calculator, it goes math, PRB, and then it's number 4. All right, there it is. I hit enter and I find that the probability of having exactly 8 hurricanes in a year is about 0.107. Remember, we round probabilities to 3 significant digits. Okay. All right, so now I'm going to pop this back up and go back to where we were. Okay, here we are. All right. So they did it in pieces. Here's the 6.1 to the power 8. Here's e to the negative 6.1. There's 8 factorial. So you crunch all those numbers and you get, again, about 0.107. All right, so there is a letter C to this that I had skipped over when we first started doing it. In this 55-year period, there were actually 5 years that had 8 Atlantic hurricanes. That's the thing we just found the probability of, right? So how does this actual result compare to the probability found in Part B? Does the Poisson distribution appear to be a good model for this? Okay, so in other words, is it surprising that there were 5 years that had 8 Atlantic hurricanes? Right? Well, not really. So we found that the probability of having 8 hurricanes is 0.107. So on average, 10.7% of years are going to have 8 hurricanes. So in 55 years, the expected number of years with 8 hurricanes is about 5.9. All right. The expected number is 5.9, and that's pretty close to 5. I'm not too surprised. Okay. It would be a little less surprising if there were 6, but 5 might be the next most likely thing. Okay. So that does seem reasonable. Okay, that's not way off of what I would expect. All right, so the last thing I want to show you with Poisson is that you can actually use it sometimes to approximate a binomial probability. Okay, you can do that when n is large and p is small. All right, and so the rule of thumb they're using is if n is at least 100 and n times p is no more than 10, which is just another way of saying that p has to be less than or equal to 0.1. Okay. So n has to be large, at least 100. P has to be small, no more than 0.1. Okay. All right. If both of those requirements are satisfied and we want to use the Poisson distribution, then we need mu. So mu would just be the mean that we talked about earlier in this video, right? For the binomial, mu is n times p. Okay. So let's look at an example of that. In the Maine Pick 4 game, you pay 50 cents to select a sequence of 4 digits such as 1377. If you play this game once a day, find the probability of winning at least once in a year with 365 days. Okay. So what I would like to do is talk about, first of all, this is binomial, okay, because the trials would be the days, and the P would be the probability of winning on a particular day. Okay. So let's talk about what's N, what's P. We'll talk about, does it make sense to use Poisson for that? Is N large enough and is P small enough? And then once we get to a certain point, I'm going to ask you to pause the video and try to use the Poisson formula to find the probability that we're looking for. Okay. All right. So the number of trials would be 365, right? 365 days in a year. There is one winning set of numbers among the 10,000 that are possible. So they did it like this from 0000 to 9999. We actually did a problem just like this when we talked about the multiplication counting rule. We talked about how many different possible passcodes are there for like your ATM card if you use 4 digits. This is the exact same problem. So another way to get that 10,000 is to do 10 times 10 times 10 times 10. There's 10 choices for the first digit, 10 choices for the second digit, 10 choices for the third, 10 choices for the fourth. Okay? So that's another way to get the 10,000. So if there are 10,000 possible numbers, the probability that you'll pick the winning number is 1 over 10,000. Okay? So n is large enough. It's at least 100. And p is definitely small enough. Okay? So we're going to use the Poisson distribution. So remember, once you decide you can use your Poisson distribution, mu is n times p. N is 365. P is 1 over 10,000. That comes out to 0.0365. Okay, so now that we've found the value of mu, we can find the probability for specific values of x. We want the probability that x is at least 1. So remember, whenever you're asked to find the probability of at least 1, it's easiest to use the complement rule. Find the probability that x is 0 and subtract that from 1. Okay. All right, so what I would like you to do if you're watching the video is pause the video and try to finish this problem. Try to find the probability that x is 0 and then subtract that from 1. And we will compare notes when you're ready. Okay. All right, so gonna find the probability that x is 0. So I'm gonna start with mu to the x. So that's gonna go 0.0365 to the power 0. And actually, if you know that anything to the 0 power is 1, you could skip that part. Okay. Then I'm gonna go times e to the power negative 0.0365. And then I'm going to divide by 0 factorial. And if you remember that 0 factorial is 1, you can skip this part. Okay. So that all looks good. I'm going to hit enter. So the probability of 0 occurrences in a year is about 0.964. We're looking for the probability of at least 1 occurrence in a year. So I'm going to go 1 minus answer. And that comes out to about 0.0358. Okay. So the probability of winning the Maine pick 4 at least 1 time in a year is only about 3.6%. Right? Even if you play every single day for a year, you're not very likely to win, even 1 time. Okay. So there's the probability x is 0. The probability x is at least 1 is 0.0358. And then I'll leave this to you to try. I'm not going to do it here, but try doing that also with the binomial formula, and you get almost exactly the same answer.